Got it. And this is the one before last lecture of this class. Today, let's just skip this slide. Today we're going to talk about distributed computing. So, bit of a new topic. We have seen how to put computing on multiple cores, how to put it on multiple on GPUs in general, how to parallelize it on GPUs, but we haven't yet got out of the boundaries of the single machine, right? So what we're trying to do today is understanding when that makes sense. First of all, what it is when you talk about distributed computing, when it makes sense, and actually how to do it in the simplest possible way. We'll introduce a library which is called Ray that helps do this with minimal change to your code. So first of all, what is distributed computing? The idea of distributed computing is that you have multiple computers working together to complete your tasks. And basically, this happens when you have too large of a task for a single server, however large that server might be. And then what the typical process that you have is that right here, your client basically schedules some task on one particular piece of the cluster. This is what we call a cluster, right? And the head node of this cluster distributes your task on the available workers that it has to complete your task, collects everything, and then sends it back to your client, right? So this is what you usually want to do. When so what are the advantages of this? Well, of course, speed. If you have 1,000 computers and you want to do a very large calculation, it might take 1,000 days to do it, and a single computer takes 1 day to do 1,000 computers. So that's a given. But it's also cost effectiveness. Some tasks you cannot do on off-the-shelf hardware. You need specialized hardware, but most of the tasks are not like that. So if you have, for example, a CPU-intensive computation, you might actually be better off with a cluster of 100 i9 from Intel, commercial grade, than to buying 10 servers that cost maybe 10 times what 10 of those computers cost, and then you spend like tenfold of what you would have with a commercial hardware. But you actually have the same or even less computing power. So this is another point: cost effectiveness. It's a good way to use off-the-shelf or low-cost hardware, put it together and cluster the computation. Scalability. The nice thing about a cluster is that if you want to add more power, you just add more nodes. So you just register another node or another 10 nodes or another 100 nodes to your cluster, and then the cluster will be more powerful in distributing the tasks that you give it, right? And last but not least is fault tolerance. If one particular node decides to crash and doesn't do its job, the scheduling will be able to recover from that. Take basically that job, give it to another node, and everything will continue to go, because the coupling is very loose, right? If you have distributed computing on multiple cores on the same computer, if one crashes, it's very hard to recover. If you have a multi-threaded application, but a single monolithic application, if one thread crash, everything crashes, usually. So the more you get loose coupling of the computation between the different parts, the more fault tolerance you have. And Ray will see probably next time some specific ways to do this. When do we use distributed computing? Well, big data processing, of course. If you have tons of data that are not even possible to store in a single computer, you need a network attached storage, and then you want to distribute it to several workers that take just a little chunk and process it and then save it back. Real-time data processing. You have an amount of requests that, for example, with an online service that requires to be answered quickly, and you cannot do it with a single server. You want to, maybe you could think about, okay, I'm load balancing on 2 servers. Yes, that's a good strategy. But when you have 100 servers, you might actually want to think about a better architecture. high performance computing, of course, simulations, so scientific research, anything complex that you might come up in a place like this that might actually require more than one computer. And also, as I said, web service and cloud applications. If you want to serve millions of people across possible multiple continents, you might actually want to think about how to cluster your infrastructure. So, example of distributed computing, let's say you run an IoT company and you have servers in every household, right? And you want to collect the data, process it, send it back. Well, you can do it with one server, usually. So what you can do is you set up a cluster that you can scale up or down depending on your usage, and then you can distribute the sensor intelligence on the cluster. I mean, of course, there's always the option to do it on the edge, directly at the sensor, but sometimes you cannot do that, or you want to aggregate data and redistribute it. So you need actually that computing power. And the more your sensors grow, the more your customers increase, the more infrastructure you need. So planning from the start a cluster that you can grow and scale, by adding new nodes, it's just a great idea. Training large models on data set distributed across many nodes. Well, that's another thing. There's many ways to do this. But for example, there's something called federated learning, where you actually collect data from different places. You learn local behavior, you aggregate it, and then you redistribute it. There's other ways to do distributed learning, but definitely is something where you want to engage in some big clusters is when you, for example, train large language models. Because beyond a certain scale, not even A2A, A100 is able to train. So you need actually multiple such servers, and you need to cluster them, right? And then you have to think about all the scheduling and so on. So you are back to the same problem. And then content delivery as well, right? If you think about companies like Akamai, when you watch a movie on Netflix, probably nobody uses something like that. So there's tons of servers that replicate the data that you watch as a movie, and that serve you based on your location in a way to streamline the communication so that you have less latency and that you don't put your bandwidth use on the whole backbone of the network, but you just put it on the last mile, because the servers already cache everything that you need locally, and then it's just serving you over the next 50 kilometers of cable. If it was one single server, or if it was a bunch of servers, but all at the headquarters of whoever is serving your data, then this data for every user will travel from wherever that is to wherever the user is. It might be across the ocean, on a fiber cable down in the ocean, which is a lot more costly than putting the data once in the remote server, replicating it once, and then giving it to you. So these are some examples, but there are more. Clustering is definitely something that is useful. It's something that you usually don't see in things that you do at the university or that you do as hobby, because UE has a cluster to run first. And second, you don't really have to solve this problem usually, right? If you do a simple demonstration at the university or a simple experiment, you don't have to deal with this kind of scale. But it's good to know what the tools are and what you can use them for. So, what is Ray? Ray is an open source tool, and it was developed by Rise Lab at UC Berkeley. It's a real-time computing lab. And it basically, my personal take, is the simplest way to distribute computation across a set of computers. It's basically, let's say, the abstractions that you will see today there are two types of things you can distribute on a array cluster. First one is basically stateless functions. What means stateless? Anybody? What means stateful? So if I write a function, say def print, right? And this is the text, and whatever here I do with my printing, is this stateful or stateless? Does it have a state? stateful statement, right? It doesn't have a state. Why? Because it doesn't save internal memory. So if you call it 2 times, it doesn't know what the text was before. But if I start writing, previous text equal, okay, text, and then I want to save it somewhere, like in self. So I have a class, for example. That's stateful now, because I'm keeping memory of the previous text, and I can use this in my next call to do whatever logic I want to do. For example, to know if I am continuing on the same line or going on this in the new line or something like that, right? So the difference in the two things that you can schedule with or distribute with array is that you can schedule tasks, which are stateless function, so basically def something, or actors. Actors are stateful objects, they are classes, right? And the idea is that you can create a kind of a session within a stateful actor. So what does that mean? Imagine you have a sensor in your infrastructure, like in your IT, users, and this sensors is giving you single readings. Right? For example, it's a temperature measurement. It gives you a temperature every 5 minutes. But you want to keep a statistics for the user. You want to keep the history of the last 2 days. Then you want to aggregate this in average and keep it for like a month or 2, and for a year maybe. And you want to be able to do math on all this. Well, you need to keep a state. And you need to be sure that the actor that is dealing with that particular sensor will be again, interface with the same sensors and will be able to give you these answers. So that's why you have actors. Otherwise, you wouldn't be able to keep this shared knowledge. You have to basically to take a centralized. If you want to implement the same thing with tasks, you basically would have to keep a central database with all the data, and then schedule, for example, a function that does the moving average of the temperature every time, and passing also the readings to this function. So you would create a lot of network connections, network traffic, just to pass the data that could be actually quite easily stored in the actor, right? That's why we have tasks and actors. But sometimes you actually want shared data to be common to everybody. For example, you are training a large model, large language model or a computer vision model, and you're training on a shared data set that is huge, right? Well, then what you want to do is have an object store that basically is managed by array, and that is not copied over for every actor or for every task, but is actually referenced directly in memory. These are always, object stores in array are always read-only. Highly immutable, right? Because you don't deal with all the problems of accessing those and using semaphores and so on. It's just too low level. Raise is very high level. It simplifies for you everything. If you want to aggregate the results, you do it using what we discussed, also for other reasons. Basically, more or less a functional method. So you don't do side effects. You return the change that you do on the data, and you aggregate it in another node, in another task or another actor, or in the main code that you have where you start everything, right? Any questions on this? Task, actor, statefulness, and so on? So how do we start a task with array? It's actually quite simple, because if I remove this part, that's basically just normal Python code. I define, for example, here a function which takes an integer and returns a square. I mean, a number returns a square. And then what I can do is just I can dispatch some of these functions by just adding @remote on top of the function, a decorator, right? And then what I do, instead of saying result equals square brackets I say result equals square dot remote I. Now, this is actually not your square, it is a future. Have you ever heard about the concept of future? Not in business investment, but in computing.
Can you say it again?
Future.
Future.
Yes.
Like the time that is out.
Like in the future, yes. Because it's in the future. That's why it's called future. Future means it's a promise. You're collecting a promise that somebody is going to tell you what the square of that number is, but it's not yet the square of the number. To access it, you have to basically do a wait, like we do in multi-threading and multiprocessing, right? And this is what the array get does. So you can start many of those square.remote, right? And then later on do all the gets. Now I do it sequentially because I'm lazy here, but I could actually do 4i in range 4 start result, and then another 4i in range 4 and print the results. Right? I could have done that in different loops because this one is like starting a thread or starting a process in multiprocessing or threading. It basically scheduled this computation on a remote node that we don't know where. I mean, it's just handled by the cluster, and it gives us a future. And with this future, we then read the result by waiting. Well, reget is an explicit blocking wait on the future to get the explicit result. Right? Is this clear? How does it work? Okay. So, well, I mean, if you want to actually monitor all this and see what's going on, you can actually start your cluster explicitly, but it's not required. You could actually run this code without starting the cluster. It just will create a cluster for you, a local one, and run the code and just then turn it off once you're done. Or if you have an account on one of the cloud providers, you could use a cloud provider for array. They are, AWS and I think Azure is one and so on. So you can actually create your code and then use, as many servers you want if you have the money to pay them, and do whatever you want for that time that you use them, and then they will be allocated to someone else. So, what about actors? So actors are classes, and basically they follow the same idea. Instead of decorating the function, you decorate the class here. This is a sensor where I have just a simple set value and a simple get value, and it keeps a state by saving this value in here. It doesn't do much, right? The idea is that something like this doesn't make sense, but if you had some heavy computation, you could have it, for example, somewhere like here. So when you access it, the computation is distributed. And the data is where the computation is happening. So you don't have to communicate that all the time. And just you transfer the data only when you have to give new input by accessing the node and calling set value. Now, let's look at this for a second. If you look, how do we instance a new sensor is by calling remote again on sensor. This will call the init. So if I had here value, here value, and here value, okay, this would actually, you would actually pass the value in the remote. Not here, not in sensor, in the constructor. You don't call the constructor. The constructor is called by array on the node where it's executed, right? Behind the scene, there's a lot of magic happening. And this code gets transferred to a new machine, it gets interpreted by another Python interpreter, and the instance gets instantiated with the value that are also serialized and passed to the new machine, okay? Then when you have to call a function, a method on this object, you receive back an object, a reference to the object, where you can call the method, but you need to call the methods with remote again, right? It's the same concept. I have a set value self value. I pass the value to the remote on the method. Does it make sense? It's a bit, I mean, you have to get used to it, but actually, if you put just remote at the end of everything, it kind of works, right? But the concept is important. This one, again, is not a method, right? This is just a reference to a method. To access it, you then need to use array. You need to tell the array that you want to access it and you want to use remote. So, and then when you want to get the result, then there is there's two times that you have to use array. First one is to access the method and tell it that you want to use it by using remote on the method itself. You don't pass anything here because the only argument here is self. Here is self, right? But then once you have this, the result of this, what do you get? You get the result? When you call get value remote, what do you get?
You get the value.
No, you don't get the value yet. You get a future. You get a promise. And to explicit that promise, you need to get it with ray. So ray get, and you now get the value out of the future, right? Always, whenever you call a method on an actor, or when you call a task, when you call a task directly, you always get a promise. So you always have to use ray get to explicit it. All right. So how does the object store work? The object store is basically more of the same. I mean, if you load an image, for example, by using a task that accesses a particular file path and then stores this image into a variable, and you return the variable, well, this is now a promise, right? It's a future. You can use this future and pass it to other methods, basically, that will use it to do the computation. This will not generate a new copy of the particular variable, and it's very efficient. So we'll see an example where this happens. So if you have a process image, which is not here because of space, a method basically that uses this image to do stuff, this will read directly in the shared memory, right? And you call it then just like this. Process image, again, remote, and you pass the reference, right? So in this case, I'm not passing the data, I'm passing the future of the data. And Ray knows what to do with it. So let's look into some example of all this. Maybe without the red stripes. All right. So let's start with something. Notification. All right. So this is the initial example that we saw. Nothing new, right? So we define our task with ray remote. So we decorate the function with ray remote, and it becomes a task. Then we call it 4 times, and we print the schedule. Okay, sorry, the futures by using ray get to access the data. So let's just run it. And you see it starts the cluster, and it tells you also where to access it, but then it also finishes and it removes that link, so you cannot really access it. So next up we'll start our cluster so that we can look at it. And then it just prints the results. And for the sake of argument, since I said I could do it, I can do it. Let's do something like this. What we can do as well is results, import this, then we do results, and then nice deal for me. And then we do for RE results. All right, so I can do also this. What is the difference? Somebody wants to explain to me what's going on here? And why does it work? So before I was calling the task on a remote node, and I was printing right away the result, waiting for the remote node to do it. What's happening now?
We are storing futures.
I'm asking for the future, and
we are saving it in the array.
In the list. And what's happening with the nodes? Are they executing in parallel, in sequence? What's going on? Right, so what I'm doing here is I'm starting this task on the cluster. At this point, I don't have any more control on what's happening on the cluster itself, right? So this really depends on the cluster, but I can assume that they run in parallel, because what is going on here is that at the moment that the task has reached the cluster, I get the future, and I'm over this line. I'm not waiting for the task to complete, right? So this means that I append this future in my list, and then I just go on to the next and start a new task. And this is rather quick. I'm just communicating to the cluster my intention to start this job, saving the link that I get back to the future, then starting a new one, saving the link back, starting a new one, saving the link back until I'm done. And I can assume that this task has to work more for the result. I mean, maybe not in this case, but has to work more for the result than me scheduling them. So when I arrive here and I start print ray get r, so I would go and look in the first one that I scheduled, it's probably not yet done, right? So I'm waiting for the first to get done, but at the same time, all the others are still running and completing. So it might be that the second is already done. The first node, I'm waiting for the first. When I'm done with the first, I right away printing the second as well because it's also done. Does it make sense? So let's rerun it again. Unless I did some mistake, it should run as well. Right. So it's running in sequence also because the function is really, really very fast. I mean, and it's running in sequence because I'm calling it in sequence. I'm not waiting for the first to be done. We'll see later how you can do this. All right. So now, in order to do more interesting stuff, we start ray start minus head minus port. I mean, this command here is what I can do to start. The one was on the presentation. To start in a new. Well, it was running already. Apparently so. Let's reset it. Please stop. Yeah, I didn't stop it. So now we have just started a cluster. And if you wanted, you were in another computer, you could actually call this cluster and say, add my node from this computer to this cluster. And you just give it the address. And if I set up a password, you have to set that password in the node, and you can just expand this cluster as much as you want. People don't usually do this unless they have their own server farm. They usually use AWS or Azure or anything like that, but they don't do it like this. But it's quite useful if you're doing research and you have some computer you want to put in that. So now we can access it, and we will do that. And this is what you see when you access your cluster. So let's see. So what you have here is the overview. You have cluster utilization. Well, there's nothing here, and plus I can install the libraries. There's no job scheduled. It's quite empty. I mean, there's no dot status and so on. But you can look at the cluster itself. So it's quite hard to move the mouse and watch this way. So what you see here is all the nodes that are waiting for you to do stuff. Basically, these are the CPUs that are there. So let's see what happens when we schedule something. Let's go back to this guy. This, have you ever heard about the Collatz conjecture? This is quite interesting problem in mathematics. By the way, if you find a solution, you're gonna win like $1 million. Or something like that. So the conjecture says that if you take any number, n, and you take the following sequence, if n is even, then f of n is n over 2. And if n is odd, then f of n is 3n plus 1. The conjecture says that if you do this for any number, you will end up invariably to 1. And nobody has proven it, but has been verified up to 10 to the 60. Okay? So it's true, at least in that range. Nobody has any idea how to prove this. Okay? So this is computational mathematics. And a lot of people have tried to prove it wrong, but basically improving the way you can compute this, scheduling more numbers and finding the first example that doesn't actually hold true. So just implemented this as a test for our distribution, but unfortunately is not that slow, it's quite fast. So I didn't go up much higher with the numbers. So what it does basically is just run this sequence through, right? Starts with n and adds it to the sequence. Then it just says, okay, if it's not 1, then I check. If it's 2, I just divide it by 2. If it's odd, sorry, if it's even, I divide it by 2. If it's odd, I do 3n plus 1. And I save it back to the sequence and so on, right? Right, so that's my function. I didn't remote this, just wanted to show you something that is quite useful if you have already an API and you just want to use the already API that you have without changing every decorator. You can just create a facade, right, that just implements the distribution in array. You call a new function remote, for example, in this case, a remote collapse sequence, and it just calls it. And that's it. Then what I do, I just create a range of, let's just take 100, and then I just schedule them, right? So what am I doing here? I'm creating some random numbers. Then I'm collecting my futures by using a something that we saw a lot of time, a list comprehension, right? So just call my remote on all the numbers. And then I just do this. Now this is interesting, right? I don't have to call it for each element. I can call it on the list, right? I mean, it's quite nice. And then I just print what the results are. Any question on how this works? I mean, beside the math, nobody knows that, right? So let's see what it does. That's already done. But well, basically, as you saw, it just runs through, prints a sequence, and it's done, right? I mean, this is quite interesting. It did a lot of computation in the meantime. Let's try with something a bit bigger. Maybe we can have some time to look at the web interface. No, definitely no. Okay, let's try something bigger. All right. All right, now it's an interesting problem, right? Jesus. Okay, so I guess I give up. But anyway, we'll see later something that actually runs a bit slower, and we can even do it arbitrarily slow by just putting here. Let's do it this way. Import time. I'm cheating. And then we do time wait. .1 is fine enough. Okay. Matt doesn't want that.
Sleep?
Yeah. Sorry, thanks. Thinking about wait all the time, and then I put the wait instead of the sleep. Okay, all right. So now we could go here and look at what's going on. Running. See? Good. That's what I wanted to show you. All right. So what you can see here is now your job running. So, and you see what's the total number of tasks that you have, the one that are running, the one that are waiting for scheduling. So as you see, Ray doesn't just dumbly put everything on the node, but it waits for the current job to be done before it schedules more. And it manages automatically my CPUs. So it knows I have 12 cores, so it's scheduling 12 nodes on that. So it's quite efficient. And you have a lot of ways to, we will not go into, but there's a lot of ways to customize this and decide how many CPUs you want to use, how many GPUs you want to use, and what each node should contribute to the cluster and so on. You can write your own configuration, just let it run from the YAML configuration. So this is complete freedom on it. But just the standard way to start is already a good one, right? And I don't know how much of this is going on. Metrics, yeah. No, it's not really set up for that. But anyway, you can also look at other jobs that you had before, failed apparently. So finished. So there was a problem probably with an overflow somewhere. That's why it was so fast. But anyway, so you can look at your log. There's a lot of work that has been done for you. If you do this with multiprocessing, you have to start writing code, right? To be able to check what happened with your job that you scheduled with multiprocessing. If you use Ray, it's basically all there for you. All right, so let's go back to this guy and let's stop it. And have fun already. Let's remove this. Let's go to something more interesting. And I wanted to show you now a few more ways to schedule things. The first thing that you might want to think that it's actually useful is that if you have a large amount of data, you probably want to batch things and start by saying, okay, I don't know, I have 1 million images and I have to process, all of them. You might want to send single image, but you want to send like a batch of 10, because that's, that memory goes is really nothing. So you want to balance the effort in the overhead in communicating back and forth with the effort of keeping the current images in process, right? So if you do this, if you want to do this, basically what you can do is, this is not specific of Ray, right? But what you can do is basically create your function so that they process a batch. So the structure of the code doesn't change much. What I changed here is I'm just creating here a bunch of candidates, and then I am batching them 10 by 10. So, and here are my batches. When I schedule them, I go through the batches, I put my mini batch of 10 numbers here, and then I just append the results to this array. So what you will have in the end is that, of course, when you collect your futures, you have to be careful, because this future, when you get it, is a list of results. So you have to loop two times, right? One times you have to leap through the batch to get each of the sequence that you have computed, and then you have another one looking at the single. First you have to loop through the batches. Sorry, not to the sequence. You have to loop to the batches, and then once you have where you are in the batch, you have to loop in the sequences, right? While in the previous code you have just one single batch, so you didn't have this part. You just had this part, right? And then it just runs the same way. Otherwise, again, there's not much Ray-specific code here, but it's important to remember this one is each task is scheduled on a node. So putting all of your candidates in one single function is not a good idea, because then you will not use the cluster. It's just using one single node. But also putting each element in the function might not be a good idea, because you're creating a huge amount of overhead and the function will take forever, right? So that's kind of a middle way, and finding out what's the best size of each batch is something that depends on the task, depending on what your cluster looks like and so on. So not surprisingly, if you run it, you get exactly the same result as before. It's quite quick. So move on. Oops. One button. Move on to something a bit more interesting, which is actors. All right, so actors are stateful. And here what I'm trying to model as an example for you, would be if you had an IoT system with thermometers that you have to collect data for, and you want to each thermometer to return a moving average, right? So that's a very simple statement, very simple proposition. What I do is I create, first of all, my initialization. I don't care about the first, I set the window size of 3 readings, so my average is going to be the last reading, the one before last, and the one before last, and averaged over this time. So I don't care about the first 2 readings to get precise moving average. So I assume they're just 0, and the moving average will be fine after a while. I am initializing therefore the window size. I'm initializing the temperature, the last reading, and the moving average as 0. And then to add the reading, I'll just go and substitute the temperature into last reading. And then I recompute the moving average with this formula, right? So this is a bit different from doing the computation on the last readings, but it's a lot more efficient. What I'm doing is I'm taking what I had as moving average, and I'm multiplying by n minus 1 times A divided by n plus the last reading, okay, temperature divided by n. And this is my new A. You get why? Right? This is basically if you had the last n minus 1 readings, right? That would be basically the same formula. There is a little difference that you're keeping around the memory of the previous readings as well, right? So there is a little different, but this formula is used pretty often for moving averages because it's quite convenient just to keep 2 variables and just works. And you can change the window size, and then we'll just change this n and this n minus 1, nothing else. So this is quite convenient. We are doing this. Then when you want to get the moving average, you just read the status of the actor. You don't have to do any computation here. Make sense? Because I pre-cache the moving average when I save my last temperature. So I do computation only once. Now, of course, if I'm not reading this often, this is a waste of computation, right? On the other hand, I'm saving space, so I'm kind of reading it already. And otherwise, I just would get last reading in case you want to see the last temperature that was recorded. So how do we initialize all this? Well, very simple. My actors are initialized by taking the class and calling remote on it. Since I have no initialization variable on the init, I just call the empty remote on it and just do it 10 times. And then I have my list of actors. Now I can play with these actors. So I can go and for 100 times give them basically, I loop through them and I give them basically a new temperature. So I take a random temperature and I just save it. Now, this is a very, very bad thermometer that randomly go from -10 to 40. It's not very reliable, but who cares? This is just for demo. So I add the reading and then I get the moving temperature and I print it. And then I sleep for 2/10 of a second, right? So is it clear what's going on here and how it works, how it's working? Right? Every time I access one of these guys here, every time I'm accessing one of these guys, what's happening behind the scenes is that this random temperature gets serialized, gets sent to my node. The method on thermometer add reading gets called by the node executor, by the node interpreter. The temperature gets passed, right? And now when I call this again, the node go and calls get moving. The result gets serialized, but I don't get it yet. I get first the future when I issue this command on the cluster. And when the result is done and serialized, then this one execute, because I'm waiting here on the future until the future is explicited through the computation on the cluster. I don't get past this line. Does it make sense? All right, and then I just loop through the rest, right? So here I'm waiting for each result to be actually completed before I can move on, because I'm waiting for the ray get. So it's actually sequential. Important, because you might think, yeah, I'm printing the result to see how it goes. It's not, you're blocking the whole computation, right? So we do it here for demo, but don't do it. So now it's going through sequentially. And it's taking its time. Now, for the sake of the argument, let's do this. It's so smart. There we go. And let's try it again. Here's a mistake. Please. Should be done a lot quicker. You see it moving quicker? Because it's not waiting for the execution every time. I mean, it's slightly quicker because the process is very, very fast, right? But it is actually more efficient. Everybody clear what is changed if I put the print inside here, or I put it down here? But this is an important point. So if I start the reading remote like this, so git moving average like this one is a future. If I take the future and I store it in this list, it's still a future. This list up here, still a future. So I'm not waiting for the process to be done. I'm just storing the promise and moving on. This is instantaneous. I go to the next thermometer and do the same. And I put them all here, and in the meantime, they can start doing the computation. Then I go through them again, and in the meantime, they should have done some computation, and now I print them one by one. In this case, I was actually waiting for each of them. When I put the print up here, I was waiting for each of them to be done because I had this ray get average right here. So they were waiting for the cluster to be finished with the reading before they could move on, before I could schedule the next one, right? So, move to the next. I think I should have removed this. Yeah, there's no value in this example, sorry guys. Just old. All right, so now let's see something with using the data storage, the object storage. What I'm doing here is I'm reading an image, which is a nice picture of the Colosseum, and I am loading it with this function, which is a remote task, using PIL, creating image data, and getting back a loaded image reference. Now this is, since I loaded with the task, this is now in the object store, and I can pass the reference to my, process image, which I call here. And the process image is going to take the image and make it grayscale basically. So do the mean on the last axis, which is the RGB channels. Does the code make sense? This is an image, so it has 3 dimensions, no? W, H, actually the other way around, and the 3 channels, RGB. So if I do the mean on the second axis, I'm going to get grayscale, more or less. I mean, usually it's multiplied by a certain coefficient, but this is a dumb grayscale, it's good enough for us. So once I've done this, I have the grayscale image, I return it, I do actually get on the return it, I do get on the future, I get the image itself, and then I just plot it. So again, I'm just going through these concepts more than one time because it's quite new, and I want you to be sure. I want to be sure that you got the main points. Any questions on this? What's going on? Right. So future, future. These are all futures. Nothing happened yet. It happens when I do this. Actually, when I do this, I expect that this guy is going to at some point access the shared data. But I don't know anything about it. I just pass the reference and let the cluster deal with it. Right? So let's run it. And wait a second, did I delete the image? Should be there. No such file directory.
Lecture 10, maybe.
That's interesting. Just ran it like a second ago. What did I do wrong?
Shouldn't you go to the source, then lecture 10 folder, then data, then?
Yeah, but it actually is on the right place. This is the right file. So dot data is actually going to the right spot because I'm running it inside lecture 10, and it should be going there, and it is there. So that's quite interesting. No, that's a file directory. Let's stop the cluster and try to run it locally directly. Let's see if I had some problem with that. Look at that. For some reason, the program is destined right. All right, forget about it. Anyway, so what it did is basically did the mean on the whole image, save it on a grayscale, and then just showing it, and there it is, plot with matplotlib. So just to give you an idea, this is the duration, right? So again, why do you want to use this? Because I mean, in this case doesn't make sense, but if you want to have again a data set with a million of those images, you want to actually share it with the cluster. You don't want the cluster to copy those images every time they use it, and every node actually should access it in the best possible way. So only the part that are used by the particular machine are going to be copied over if needed, and so on. All right. So move on. And the last example that I have is actually our beloved weight. So far we have been using reget to do everything. Now this is quite a simple example. We're generating 100 by 100 random images. So 100 by 100 pixels, 100 by 100 random pixels. And what I'm doing is again, I'm turning it to grayscale. And to do grayscale this time, it's just a bit better grayscale system that is using a weighted sum of the pixels. So just nothing important. What is important is that I'm processing this line by line. So in this case, again, it doesn't really make sense. But if you have a really, really big data set, you might want to slice it and want each worker working on a particular slice. How do you do that with this? Because if you are processing, for example, numbers and printing the result, right? You can do it as we did it before. But if you want to actually do a weight on whatever is processed first, and add it to your aggregated data, and then move on to the next one, and so on. Actually, that's not a great strategy to order them in the weight, because then you might wait for something that is actually one of the last to be done. So what we do is here, we do this. Remaining future, least future, and then we show that while remaining future exists, we do ray weight on the remaining futures. And this gives me two things. Gives me what I actually want to process right now and what it's done. So the right. So first of all, the process line, again, this is a future. So the process line, you have to get it out of the first variable, and this gives you the index on which it was scheduled. And then basically printing the result. I mean, but before that, you get again. Okay, sorry, I wrote this yesterday. Forgot what it's doing. Yes, so the line exactly. So the line index, you get it from futures index, and the process line is the explicitation of the future itself. And what you do is basically you take the grayscale image and you substitute for the line index the process line, right? So in this way, independently of what gets done first or last, you always substitute in the right place, right? So this way you can do it out of order. That's basically the great advantage of instead of doing a loop in doing gets. So this tells you what is ready, and you can then move on, right? By just processing here, done, right? This one. And that's all you have to do. The rest is actually the same as before, right? So if you look into this particular function, in this case, it's taking just one line. So it's a matrix with just one line, but 3 channels, and it's multiplying each vector of channel by this particular vector to create a weighted average. And when I schedule them, before I do anything else, I take the image and I split it into lines, right? So I fix the height index, I let the width index run, and then I collect everything else for that width into one particular matrix. This is now a list of matrices. Each element is a line of the original image. Does it make sense? So when I need to then schedule them, I do again a loop into the image lines, and I schedule process line with remote on each line. Now I have a list of futures. And this list of futures, what I go and wait on, and I get each one that it's done, I get it one by one, and I print it out, and I insert it into my result, right? So we can run it. And it's done. I mean, it's quite quick. Yeah, it's now it's not active anymore because I didn't have the cluster on. Yeah, pity. Well, anyway, there was nothing much to see. What happened in the meantime is that the cluster worked through the lines 12 by 12, right? Because it has 12 nodes. And when it was finished with one, this loop was executed. The processed line gets inserted into the grayscale image here, right? And then it goes back into waiting. And when it's done with another one, it will again insert the grayscale image and go back into waiting until the cluster is done with all of this. Then this is a false, and then it goes out. Right? It's quite simple. So we're actually done for today because I don't want to introduce more concept. I think this was dense enough. I see at least one face that I didn't see yesterday.
Ali.
Okay, then we know why. Which means everything is fine because we have the presentation for you today, and I'll see you all next week, and then on the 12th of August.